And welcome again to Tutorial Day, and our first tutorial is this well-lettering...
This person here.
This person here. This person is well-lettered not only in knowing where the cafes are in Monash Caulfield, but in graphical models for machine learning. He's been at NICTA a while ago, and he's more recently working at Monash, and he's going to tell us all about non-parametric Bayesian models.
Okay.
So, over to you, Ray. Can we get you lapel mic'd up?
Oh, yeah. Sorry, I should have done that earlier.
That's all right.
Sorry, I literally got out of bed at 8:30 after 12 hours sleep. I got off the plane from China, so I'm really in a daze. I just hope I can figure all of this out. Thank you. Are we good? Yep. Ooh, we're on. So I was going to try and bring a map up. Caulfield map. So I've got various levels of introduction here, and I'm not really sure how much I have to introduce to people. I'll bring up the Caulfield map before we break. So just some advice. I'll try and hand these slides out at a later stage, but I do colour code things. Red you've got to watch out for. Green is usually new. And some things have a really good Wikipedia entry. So the things that have a good Wikipedia entry I've marked. Some things the Wikipedia isn't much good. In one case I pointed to you to say, oh my God, this is terrible. Of course I haven't sat around to fix it up, so I'm not no good, but anyway. Most of this, I'm going to skip through some of this. I'm going to assume people know a little bit about graphical models and basic distributions. Now, I'm sorry for those of you who don't have much of that. There's only so much. But we will look at the motivation a bit. So very briefly, parametric methods. That's hopefully what some of you have seen. Fixed number of parameters, standard linear regression. Sometimes we can add a dimension and say we're also fitting the dimension. So that's a good, typical thing we do for parametric methods. Non-parametric methods, if you look up an early non-parametric book, it means there's no parameters, like k nearest neighbour. Then there's a completely different thing, which is usually called Bayesian non-parametrics. And sometimes that's called an infinite number of parameters. And if you were a real hero in the early 2000s, you'd get the word infinite into your paper title, because that just showed how good you were. Not many people are infinite. And, well, in fact, they weren't, because what they're doing is a variable number of parameters, and you unroll more parameters as your data requires it. So it's not actually infinite. It always gets them when they go to implement it, that infinity. So what do we mean by an unknown number of parameters? This is the way I usually like to think of it. In this case, there's some fixed number of mosquitoes, right? But we just don't know it. Is it 8? Is it 10? Well, we're not sure. Maybe every millennia or so a new mosquito might arise, but not a big deal. In English, we all know better. For every gigabyte of text you get in a corpus, you get more words. They never stop coming. So it's not that you have a fixed and unknown size of dictionary, it just keeps getting bigger. And that's what we're really dealing with when we mean a variable number of parameters. Music is a better example, and this just isn't songs, this is genres. Genres keep on changing. So non-parametrics is where the dimensions keep on growing. Now, I'm not going to be looking at trees and stuff, but all of this applies to trees, usually, in limited ways. The models I'll be looking at deal with these sorts of things. So I'm not dealing with these. Well, I do. In our research, by we I mean students and other staff, we deal with all of this. But what we're looking at here at the most is a matrix. But these are the sorts of things people are using this for. Ever expanding number of items. So we need probability vectors to list possibilities. We need parameter vectors. User preferences, people use them for layers of a deep neural network, and those vectors are unending. So now this is an example of some of the stuff. You don't have to know all of this, but it's kind of handy in some cases. I'm assuming that you know the basic Bayesian paradigm, which is a prior and a posterior, and a likelihood. So I won't be doing any of this Gibbs sampling stuff. We won't have a bit of it. You'd be glad to know. But this is how I like to think of the area, by the way. I gave a little bit of this talk in Singapore, and no one had ever seen this movie. I hope you've seen this movie. It's kind of fun. Who shot? I'm not bad. I was just drawn that way. Well, I'm not complex. I'm just written that way. So that's how I think of this field. This is a quote from Lancelot James. This is how they introduce a Poisson process. We're going to do it a different way. So we'll not be looking at Borel sigma fields and such. I don't think they're necessary. But this is ploughing through this stuff is one of those things that you're presented with if you want to understand some of the good theory. So this is, in fact, this is an amazing paper. This is really good. But you're presented with this at the beginning and you kind of wonder what you're getting yourself into. So I took a holiday in July and I read this paper and a few others. I think I must have been crazy, but anyway, that's what I did on my winter holiday. Okay. Non-parametrics lets us deal with a variable number of parameters. The Bayesian inference side of it. We do that not because we have to be, not because we're religious Bayesians and, you know, God told us how to operate, but rather it's just a good engineering approach. Sometimes it helps, sometimes it doesn't. Sometimes it's practical, sometimes we're less Bayesian. You know, most of what I see, regularization, any of these methods, it's no different. Anyway, this is just a philosophical side of it. So, discrete distributions I'm going to skip. I'll just mention the names so that you've got them. Multinomial, we'll be dealing with multinomial data. Has this likelihood form. That's the choose function, which I don't think we'll be looking at too much. There's the binomial, which is the binary version of it. If you've only got one data point, it's called a Bernoulli. Poisson. We'll be playing with Poissons a lot. I'll be doing some plots in a minute. The Poisson variable is the rate. So hopefully you've done it in things like arrival times. You're waiting at a lift and how many people arrive within 2 minutes. You've got a Poisson rate. So computer scientists usually have done Poisson distributions in their undergraduate. It's used a lot in CS theory. The Dirichlet distribution is looks like a multinomial, but it generates a probability vector. And I'll do some plots just so you can see. It's got a parameter vector, which is really a mean multiplied by something. So if we normalise the parameter vector, we get the mean of the probability vector. There it is there. In a discrete sense, it's very much like a Gaussian. So a Gaussian has a mean and a variance. Well, a Dirichlet has a mean and what we call a concentration, which is the inverse of a variance. And a Dirichlet, like a Gaussian, can be symmetric, the same in all parameters, or different. Here are examples in the one-dimensional world. So we've got two dimensions in our probability vector. And if we have a very low concentration, we get a high variance. The variance is so high that all the weight's up the end of the 0, 1. And as we increase that concentration, our distributions slowly get pointier and pointier. In the three case, this is the domain of our vector. It generates vectors in this space called a simplex. This is the formula. This thing here is called a beta function, and it's constructed from gamma functions. But there's the mathematical form, and if you just have 2 instead of 3, you get these guys here. With 3, this is what it looks like. So if everybody's 1, it's uniform. 1 minus 1 is 0, strangely enough. If it's uniform but all the alphas are quite high, you get it something focused. It can be very diffuse if the values are low, 0.8, 0.8, 0.8. See, it's now focused around the edges. But the way I like to think of a Dirichlet, and that's the main take-home I want you to get from this, is it's just producing variance. So here's my mean of 4-dimension, and if I have a high concentration, which means a low variance, the vector I'm sampling is going to be almost the same as the original. If I have a low concentration, 0.5, then the vector I sample can be very different. So that's the idea of the Dirichlet. It's letting us sample probability vectors. Similar to, or a long way away from the mean. Now, this is the final bit of this introductory stats part. There's the formula for the Dirichlet distribution with that beta function and the 2-dimensional case. We've also got something called a gamma distribution, which may be new to a lot of you. So a gamma distribution, in a sense, is sort of so a Dirichlet is to a multinomial as a gamma is to a Poisson. This gamma distribution is the natural counterpart, if we'll go back to the Poisson. There it is. Lambda to the x, e to the minus lambda. And lambda is our parameter. And here we have lambda to the something, e to the minus something lambda. So they kind of go together. So if you put a whole lot of Poissons together in a likelihood, it takes the form of a gamma. And that's why we have to deal with it. So you may have heard of latent Dirichlet allocation, which is what happens if you have put a multinomial with a Dirichlet together. Someone else has figured out that that's the same as having Poissons and gammas together. So they all kind of complement each other. This is a little statement, and then we'll get on with our graph part. Oh, sorry. If we normalise Poissons, we get a multinomial. Same thing as if we normalise gammas, we get a Dirichlet. So if we have a vector of these gammas, lambda k, a vector of them for 1 to k, we compute their total and normalise that parameter vector. It's the same as if we had a Dirichlet. And the total is also gamma distributed, summing on that first parameter. This is a very important property, and we'll see that this extends to some more abstract cases. So, graphical models, quickly, I'll assume you know about this. The plate extends means a series, it's like a vector. Two of these boxes means a matrix. The grey ones are the known ones, the data. We build up a mixture model from the parts. So there's a latent variable z that gives us, let's see, I think I've got the formula here. xn is distributed as, oh, this is a whole LDA. That's a bit, let's do this one. Latent variable x, its distribution we get from this latent variable z. The parameters to the distribution come from a vector theta. This latent variable z is generated from this vector p, and here we have it. In form, we generate our latent variable from this probability vector. We generate our x from the thetas. Oh dear, my thing's, oh, bloody hell. Like not changing. I'm going to skip that. Feature matrices. Right. This is data. Right? The grey stuff is 1. The white stuff is 0. Rows. Document or image. Columns. Words or features. We'll be looking at this matrix a lot. Doesn't mean we're playing with the data, but you've got to have the idea of this. Columns are features, rows are documents or items. The data could be counts, right? It could be 2, 5. So, oh dear, sorry. That's the feature matrix. Now, this kind of data you'll find embedded in many things, all right? So, the music genres, the graphs we do with this, if we're doing citation graphs, it's a big matrix. So this is the kind of data we'll be sort of playing with for most of the time. You could have counts if you're saying how many input nodes are there, or how many times have they watched this particular music video or music track. This is a discrete feature matrix which we'll be working with. So other versions, the counts, where you've got the zeros. Some people will also use the Boolean, and when it's non-zero they add a weight to it, so they generate a Gaussian or something, and this would then be an input matrix for a neural network. So you've got these different combinations. Now we can order the matrix. So the idea here is that we're not seeing all of our features. So think of it as a word problem. Documents are coming in. We haven't seen the entire dictionary yet. It's still arriving. So there's going to be a whole lot of zero columns to the right of our matrix that we haven't seen. But this is the model. In this case, it's Boolean data. Boolean data. I is the row, K is the column. Sorry, my fingers are... It's a Bernoulli, and so our big question is, how are we going to model this? So we know we've got Bernoullis on each column. In this case, well, all we know is there's words we haven't seen, but how many? The big question. What's K? We don't know. How many unseen words are there? Bit of a problem. It could be a whole lot of those unseen words, and we don't really know what it is. And how are we going to model that K to do that? That's the question which we'll be looking at next. So that's the background stuff. Now we're going to get into some basics to deal with what are called processes. So this is someone else, you know, someone went off to get me a coffee. I'm kind of worried because I haven't got back. Oh, there you are. Gosh, how long has that been there? Huh? I hope not. Thank you. All right. No, it really is. I went to bed at 8 o'clock and I crashed and woke up at 8:30 and I thought, my God, where am I? Pardon me, I won't eat that till afterwards. It smells really good. So, foundations. This is where we're starting to get into the process part of it. A Poisson point process, that's what I'm going to teach you about now. They're really simple things, and there's some complications. We won't get into the complex part of the theory. I'll point you to it at the end. But they're handy because they let us do two major classes of things. One is to deal with this variable number of parameters. We can use Poissons. So we can put a Poisson on K, and that's what we're going to do, on how many rows or how big our dictionary is. The second thing this is used for is for time-varying or space-varying events. So what I won't be doing, which I probably should have done, was to look at Hawkes processes, which is the interesting thing that people have been playing with recently for burst data, like Twitter data. But it's also used for crime incidents in a city, for instance. So all the police departments in the US now use crime prediction software that's all based on Poisson processes, spatial or time. So here's a spatial process you can understand. There's two parts to this. One is the points in location, and that's spatial. So where does the point appear? The other part to it is the size of the point. So on a spatial process says where on the map and what's associated with the thing on the map. And the process part we generate with a rate. And in this case, it's going to be how many earthquakes per 100 square kilometres in 1 year are we going to get. So you'd have an intensity or rate like that. If it was uniform on the planet, it would be uniform on the map, but it's not. We all know earthquakes sort of tend to congregate around the zones, whatever they are. And these have been marked with their magnitude. There's actually a colour. I don't know what the colour is. So maybe it's depth or something. It doesn't matter. But so they're marked. And that's done with a probability distribution. The first part of it comes from a Poisson rate. The second part comes from a probability distribution. Number of earthquakes in 2014 per unit area. That would be our rate. And we know that geologists have probably got a very uneven map that has that rate on it somewhere. There's an abstract version. This is what a mathematician likes to think about. Any more complex, you've got problems. So here we have points in a 2D space. Now, the abstraction here that I want to mention about, is how many points are inside this oval. So we've got a statistic, that we're going to use at times. This oval is the set B. And how many points for our process are inside that oval? NB. So N is a counting. It's sometimes called a counting process, but it's just going to tell us how many things are inside the given set. You can imagine that if you know NB for every set B, you know where the points are in sort of an abstract sense. There's something called a spatial process, which isn't really anything. I don't know what this definition says. It just says you just get a collection of points. A spatial process is a collection of points. Wow. So, but that's what it is, apparently. But the hard bit is, how do you generate those points? So where do they come from? Well, we'll get to that. Bit of an aside, we have something called a Poisson distribution. The Poisson distribution has an amazing property, very important, and I'll illustrate it. So, if we can add two Poissons together. So if we add the parameters, lambda1 plus lambda2, and generate a variable from that, it's the same as if we generated the variables independently. So this is an additivity property. So let's have a look at that in figures. This is also called, if any of you have done first year stats, this is called infinite divisibility as well. Now, it's a very common property, so it's actually the property we're going to use to generate processes. But let's see what it means. Here are two examples. If we add the red and blue distributions, we get the... if we add the blue and green distributions, we get the red distribution. So we add them together, but then we normalise them, remember? So that's why it's smaller, in case you're wondering. And so here's the distribution with the parameter lambda1. Here it is with 5. And if we add the two parameters, we get 6, and it's the same distribution as adding the other two. So you can kind of guess, I hope, what happens to these distributions. They slowly get lower and lower. And on this end, they're pointy, and that end, they're actually very close to Gaussians. And that comes from this additivity. Now, the gamma distribution and some other distributions does the same thing. So it's got more or less actually very similar shape. We start at the smaller end with the small lambdas, and we can add them, keep on doubling them, and you can see it all naturally fits together. And that's because of this additivity property. I'm going to introduce something called a measure. This doesn't mean we're doing measure theory. If you're in statistics, you spend 6 months, I think, doing measure theory. I did way too much of it doing Lebesgue integration. There's something else I forget. But in math, they do integration. In statistics, they do measure theory. And they spend way too much time on it. God knows what they use it for, because I've never seen a use for it other than this particular statement here. I'm probably insulting the statistician here. So probably not. But the idea is a measure is just a property on sets. It's additive, right? So M of A union B, if they don't intersect, is equal to MA plus MB. And if you add that with M of the empty set is 0, you've got yourself a nice function, and it acts like a size. So it's a function that gives us size. In the world we normally deal with, the engineering world, it's just integral. A measure is an integral. So you can imagine any function can have an integral, so there's just a huge number of measures. It's not like there's 6 or something. So it's a non-negative additive function is a measure. It's just the size. And if it happens to add to 1, if the whole measure it gives you 1, it's a probability density or a probability mass. Okay, that's it for measure theory. So why are these two things important? Well, a Poisson distribution is additive in its arguments, and a measure theory is additive in its arguments. So put them together, and we've got stochastic processes. It's a Poisson-based spatial process. So let's look at that in a simple case. Here's our domain X. We can split our domain X into 4 parts, A, B, C, D. We can say, well, the total number of points in X is going to be this. Nx is a Poisson based on our measure of X. And what this additivity says is we could have built that up from the parts. So instead we could have taken MA, MB, MC, MD, taken a Poisson on them, got NA, NB, NC, and D and added them together. So all of this additivity of both the Poisson distribution and the measures sort of complements stuff nicely, and it means that you can... So what we have is, with this measure, we can now define how many points we have in a given set. So if we want to generate points according to this measure, what we do is we just break our big set up into small parts, generate the number of points in each part, and we've got an approximation. So we just put a grid on everything and apply the Poisson to each element of that. So here's an example of a spatial process in a constant world. Here we have it's a uniform, so it's a uniform rate of 100. The size of the box is 1 by 1. So that means the total number of points in there is going to be Poisson of 100. So that means there'll be 100 plus or minus 10 points. That's the standard deviation. And there they are. Someone's gone and generated it for me. We could break this box up into 4, and the count in that should be Poisson 25. Here is a non-uniform rate. So in this case, the rate is a function of y, and it says there's less points as y gets larger. Now, if we take the integral of that rate, we get 217. So that means, on average, there's 217 points in this entire box. But in order to generate, we can either say, well, how many points in the entire box, or we could break it up in little bits and generate points in each bit. There are other ways of doing the generation, but this is just the conceptual way of thinking about it. Now, another actually important interpretation here is that this Poisson rate can be turned into a probability distribution. So if we normalise it, we've got a probability distribution. So in this case, our Poisson process corresponds to this. So all the abstraction goes. The Poisson process is that we're going to generate n points according to this Poisson distribution. Then each point is going to be generated according to this probability distribution. So while we defined a Poisson process abstractly in terms of every subset has a Poisson distribution based on the measure, well, in practice, it's just, we'll generate a number of points according to a Poisson, and then we just go back to regular old high school probability theory to generate the points. So, so Poisson processes, in many cases, are not that mysterious. It's just a probability density function. Now, here it's even simpler. There's actually 4 dots on top of each other here, but you can't see them because I don't have a 2D plot, 3D plot. In this case, there's 12 dots on top of each other. So this Poisson rate is a delta function, and it's only got value at 4 points. So in this case, instead of it being rho, we normalise rho to get this kind of probability density. In this case, what's going to happen is, the Poisson process, what it does is it just breaks up and says, well, in fact, you've got a Poisson at each point. So if you've got a delta function in your rate, it just says, well, you've got a Poisson. So this kind of rate degenerates into just a Poisson at all the points it occurs at. Now, there's one other thing we have to deal with, which is infinity. So there's our formal definition. We've just about done it all, actually. You wouldn't know it, but we did additivity, which is what Borel's sigma fields is all about. This bit applies for certain, well, anyway, I'm not going to confuse you. Confuses me, just in case. Definition of a Poisson point process. This is sort of a simplified version. So it generates a countable number of points for any subset of the space. We take the integral over it. Then the number of points in that subspace will be distributed as Poisson. And for independent sets, the numbers are independent. So this is how we use a Poisson to define this Poisson process, but as I explained earlier, it's in fact just operating like a probability density with a total. Here's a really simple case where our domain now is a 0, 1 line. This is the probability, This is the probability density here. This is a Poisson rate. Now, the only thing is the Poisson rate doesn't normalise. So it could be 1,000 times, 100 times less. You know, it doesn't matter. So the PDF must normalise. The rate can be any number by the PDF. So, and what that means is, in the shaded part, which is the range is here. There it is. It's got an area. I computed it, 0.385. The wonders of Python. And our Poisson rate is 3 times that. So the chance of getting a point in here is 0.385. That's also our chance of getting 1 point in here, but we know we've got 3 times that. We have on average 3 points in this entire region. So on average, we're going to have 3 by 0.385 points in this region here, which is about 1. The thing about a Poisson point process is that you can have an infinite number of points. And that's quite easy to deal with because we're just going to use additivity. So what we do is, in this case, I haven't shown you the function, but the function goes off to infinity at the 0 side, and it won't integrate because it's infinity there. So all we're going to do is partition our space up into smaller and smaller bits on this left-hand side, to smaller and smaller pieces, cut it up. Every slice is finite, but if you add them all together, you get infinity. So, and now we generate the number of points we're going to get in each slice. Because we know by additivity we can break it up and do our Poisson process stuff on each part independently and put the results back together. That's what additivity gives us. So we can deal with infinity just by breaking it up. So here are the three cases. The discrete case is where our rate is not a regular function, it's a point. It's got a number of points. It can have an infinite number of points as long as it's countable. In this case, we're just going to generate nk points at each xk. Here's the finite case where everything's simple. We just generate n points according to a process. We generate n according to a Poisson, and then each of those points we generate by the scaled rate. And in the infinite case, we just partition up our full space so that the integral of each part is finite, and then we apply the previous. So there it is. So that's how we deal with a Poisson point process in the infinite case, and that adding them up is called superposition. When you're dealing with processes, it's called superposition. When it's functions, it's additive. I could never figure out the difference of the word. So there's our definition again. So it can work with a rate function that integrates to infinity. We just have to be able to break up the space in a way. All work's due to additivity of that Poisson distribution. Depending on what context you're working in, there's different terms here, intensities, Levi measures. Levi was an early mathematician, I think the 30s or something, who did a lot of this early work. Usually the points are called events. So that's our key little bit of math. But, you know, we actually don't stop here. I've talked about a Poisson point process. You can have a gamma process, a stable process, a Dirichlet process. They're all done in exactly the same way. No difference. We take this definition and we say n is now going to be we replace the distribution here by a gamma or a stable distribution. I think a Gaussian even works, but I don't do that. So any distribution that's additive in its arguments, we can plug it in there and we've got a different kind of process. But as I was saying before, for the Poisson point process, that's not a constructive definition. It's a conceptual definition. It shows us how it works. But it doesn't give us the math we need to do inference with these sorts of things, to put it into a likelihood function. What's the likelihood function for our points or something? So to do the math we need a different kind of definition. So that's what we'll be looking at after this. I'm going to have a bit of a side, and this is so we can do the... I've got a bit of a rant in the middle here. You ever had a rant in a tutorial? You probably haven't. So hierarchical Dirichlet process. That's the one that caused all of the noise and publications in the early 2000s, late 2000s. So Michael Jordan, he had a joint appointment, stats and computer science, and Jim Pitman, who's actually a Canberra boy who left early and went off to Berkeley. Jim Pitman is the king of a lot of this stuff. He does work. I remember we submitted a paper early on, and someone said, "Oh, that formula you've got there, that's equation 212 on page 515 of Jim Pitman's tome." You know, so we realised at that stage just about every formula we'd ever created had been produced already by Jim Pitman. It's just that you could never find them. I'll show you an example in a minute. So Michael Jordan got onto this stuff and he started selling it. So he's sort of the research version of a salesman. So he was selling this along with a few other things at the time to the NIPS community, and they bought it. Actually, a very nice tutorial. I'd recommend this one by Wray. So Wray seems to have gone over to the dark side, or he had for a while, and now he's gone over to the other dark side. So he was a computer guy, and then he joined the stats department at Oxford, and now he's gone off to Google DeepMind. So he had one of the early deep neural network papers. That was. This is what he was looking at the time. He still does this stuff occasionally. He did a paper a couple of years ago. It's quite a good one. A Dirichlet process. So Dirichlet process, it's what happens if we replace a Poisson by a Dirichlet in that definition before. So what we're going to say is if we break up our space, then the distribution of a Dirichlet process looks like it would be a Dirichlet on that finite partition. So if we go to this little place here, this picture of boxes here, where is it? There. So if we've got a Dirichlet process operating on here, then a Dirichlet process gives you a probability vector, and everything's probability vectors kind of add. So any Dirichlet process on this X, if we look at the resulting probability vectors we're generating on A, B, C and D, their distribution looks like a Dirichlet. So it's more or less the same, but we replace Poisson by a Dirichlet, more or less. That's about all you need to know, because we're not going to go into the more details of that here. But it's defined similarly from the top down, not constructively. You're not given a formula for doing it in a real sense. You're just saying that the Dirichlet process on your infinite domain, so here it is a natural extension of a Dirichlet to arbitrary probability measures. So there it is. Now, and here's an example. Our measure, our input measure, in this case is a Gaussian. So that's our input measure, and our Dirichlet process is going to take this and output this. So what this is it's a probability vector. Oh, what happened there? Sorry. This is a probability vector, which means if we add up all of those weights, we get 1. But the weights are only on at certain places. And the points on this space here have been drawn according to this Gaussian. So the points are drawn according to the Gaussian, and the weights are computed according to this magical Dirichlet process. So that's what a Dirichlet process is doing, basically. This slide comes directly with a few modifications from an earlier slide from Michael Jordan. And we would use these in a mixture model. So in a mixture model, we want to have different Gaussians. Well, we'd start with this. What we get is a probability vector over points, and this would then be all of our means. So this represents all possible Gaussian means. And now for an individual point xi, it's going to pick one of these with probability proportional to the height. So it'll pick this particular one as its mean. So Dirichlet processes was used to create mixture models. And so we had infinite mixture models appearing in the press. Something didn't get changed, right? That's okay. So this is what the output of a Dirichlet process looks like. It's a distribution on X. This is the distribution on X. It's a Gaussian. This is a distribution on X, but it's only finite at a finite number of points. And there it is in mathematical terms. It's finite at those points theta I, and the value you get at each point is mu I. And it's a probability distribution, which means the sum of the mu i's is 1. Okay, so what happens if we stack these up? So now we're inputting our Gaussian, generating this probability distribution. Now we give this probability distribution as the measure to the Dirichlet process. And what we're going to get is variance of this initial one. So this is another early slide from Michael Jordan. I have to apologise. His version was this bad, so I couldn't find the original. I wasn't going to create it. This is artwork beyond my capability. So these three, they're all variants of this one. They're non-zero at exactly the same point. The heights vary, that's all. So while we started off with a Gaussian at our first level, our Dirichlet process then gives us a probability vector over points. Now what we're going to get is different probability vectors. These probability vectors are all variants of this one. If the concentration was low, they'd all be very different. If the concentration was high, remember, high concentration for Dirichlets, these would all be virtually the same as this one here. So we can generate different probability vectors and make them closer or further apart from the original one. So people thought this was pretty magical, and they were using this for hierarchical mixture models. So now to start with the rant. So where are we in this field? I'm going to look at some of the famous work in history. And just be aware, hindsight's wonderful. I'm working with hindsight, right? So I'm going to be criticising some work, but, you know, all due respect to my better colleagues. This is the paper that everyone cites on this. I reckon this paper is way too complex and it doesn't really give you anything useful. I would say don't read it. That's my recommendation, but it's got 2,600 citations, which is more than I'll ever get for one paper, more than I think most of us in this room will ever get for one paper. But, you know, I bet most of those people haven't read or a good deal of them haven't read the paper. in detail and don't understand what all that notation was about. That's what I would say. It's pretty hideous stuff. Most of it, I think, is unnecessary. So what's going on? These guys discovered this property and proceeded to play with it. I don't think they quite understood yet what they were dealing with. And it took us a few years to get to it. But if you look at Wray Buntine, the first author there, he's got some great tutorials on this, which I think are really good overviews of it, but I just don't happen to like this paper. Here's another example of more recent work where people don't get the idea. Online variational inference for hierarchical Dirichlet processes. So online variational inference, a wonderful thing. Stochastic methods for optimization, incredible, fabulous. But in one of the early paragraphs, it indicates they don't really understand the key thing that this method is giving them. So they're saying that we also want to determine the number of topics. Well, that's not the key power that this technique is giving you, and I'll show you in the next slide what I mean instead. So in all of our experiments, the real advantage you get from using these methods comes from something else, which is illustrated here. So this is for LDA, but just think of it as mixture models. It could be mixture models. These are the ranked probabilities of things in our mixture. So if we've got 200 different elements in our mixture, 200 components, we're going to rank them according to their frequency in the data. And for the traditional version of this method LDA, the ranking is pretty flat. Here it is if you use a smaller k. The ranking is pretty flat. But what we find when we run this hierarchical Dirichlet process LDA, one of the things we're doing is also fitting. We're saying, well, these proportions is also unknown, and we're going to fit it. What happens is, in this model, what you're actually saying is that all classes are equally likely. Now, I hope you understand in a mixture model, you do not want all classes to be equally likely. If you're doing PCA, for instance, it's well known in principal components analysis that the proportions of the components drops off exponentially. That's what makes it work. That's why people use PCA. It's the same with this. There are some high frequency components, there are some low frequency components. Just think of a mixture model. Not everything is equally likely. And you'd like to fit those proportions as well as part of your statistical activity. So this is what we find the hierarchical Dirichlet process LDA is doing. It's also letting you fit those topic proportions. But that's what the experimental work shows you very, very strongly. So this is how I like to summarise about 5 or 6 years of research in LDA. So just think of mixture models. Initially, you've got mixture models and you say all topics are equally likely. Then you've got a concentration parameter of this Dirichlet here, and you're now going to fit that concentration parameter. So you don't have to read these graphs, but the only difference between these two is I've unshaded this one, which means we're now fitting this parameter. And now we're going to turn this parameter into a vector and fit the entire vector into it as the single point. This is where we mean we're also fitting these proportions here. So we're also modelling what the probabilities of these are. So this is the vector we're fitting, this one here. This was a paper, Hannah Wallach, David Mimno. For any of you who do LDA, I hope you know the best known package is something called Mallet. Originally by David McCullum, but David Mimno now at Cornell is the one who maintains it. This is what they discovered in 2008, and they released this package that did this, fitted this. You know, there's no non-parametrics here. This is just pull out the usual tricks that machine learning people do. Here's a vector, we want to optimise it. Oh, well, okay, what's the likelihood function? We'll slap an algorithm on there. They did a few tricks to make it work fast, but otherwise it's pretty stock standard stuff. Works incredibly well. So there it is. There's our model that these guys had done. This is the model for this hierarchical Dirichlet process LDA paper that got the 2,600 citations. 2006, right? So it predates these guys, but here it is. What's different? You no longer have a finite level that you're going to, so K is now infinite. The other thing that's different is that you've replaced that Dirichlet by a DP. So Dirichlet is a finite thing. If you want to have an infinite probability vector, we use a Dirichlet process. So that's the difference between these two methods. So usually what we call this is a truncated HDP LDA. And there's a whole literature on that. So these things are virtually the same. This is just a truncated version of this one. But this is how it appeared in the paper. So in the HDP LDA paper, they showed it this way. That's what their diagram looks like. And it's hard to see that it's actually the same as this model over here. And you'll still see papers where people are putting all these models up and you're trying to figure out what the hell they're doing. But if you remember, once you go, what this is, it's a hierarchy of Dirichlet processes. There's a Dirichlet process and a Dirichlet process. But once you go below the top level, it becomes a Dirichlet. A Dirichlet process becomes a Dirichlet below the top level. So this is, in fact, what you have. So we had all of these papers where people were producing ever more complex algorithms in the early 2010s. But what was fascinating was in 2009, they'd done a paper that is a truncated version of the same thing, was 10 to 100 times faster, gave huge quality improvement in terms of the accuracy of the model fitting. So it was just better in every metric, better in every possible metric. But none of these guys realised that they were actually doing what these guys had done. I emailed these guys in 2013, you know, David, did you realise you were doing a truncated version of HDP LDA from the famous 2006 paper? Oh, no, I didn't realise. So took me a while to realise, but so the interesting thing is that all of this sequence of very complex mathematics was just blown away by this very traditional bit of machine learning down here. Here's another example. So this is what I'd call complications in the non-parametric community where, you know, there's better ways of doing things and other ways of thinking about things, and people are doing unnecessary complexity. Here's another one by two very related groups. This is one of those earlier papers I'd mentioned. Now what people are doing, so matrix factorization is a big thing. In 2005, I think it was, people realised that something called Poisson gamma matrix factorisation is exactly the same as latent Dirichlet allocation, with a couple of minor variables tossed in. So this is an extension of that result. These two papers actually do exactly the same model. I don't think the authors realise. They work together a lot. So in their experimental work, there's no mention of any of this other work. In fact, the underlying algorithms are similar too, but no one seems to realise this. Another one of my... This really puzzled me for a while. I was looking at this paper. There's actually a classic result in this paper, in part of it, but in the title it says hierarchical beta process. And they cite this result here. No one I know knows where it comes from. So I talked to the Bayesian non-parametric statisticians, what do you think of this paper? Because I figured there was something wrong with it. It is in fact an error. So the core part of the paper is in fact a flaw. I'm not sure where they got the idea. I think it's sort of an analogue to earlier work. But so, and just to top all of these things off, and a lot of these problems come from unnecessary complexity. That's how I view it. To top all of this off, here is what I was told was one of the most important theorems, or in this case, propositions in the field. Now, this is by Jim Pitman in a paper in 1997. So Lancelot James, who helps me, he's a bona fide Bayesian non-parametric statistician. He reads all of this stuff before breakfast. I looked at this, and for about a year I was told it was very important and I needed to understand it. But I had major problems with what is a subordinator? At the time, what is a Levi measure? What does this notation here mean? Because that's a distribution, and what the hell is this? God knows. What is all of this? So for a while, for about a year and a half, I was just, this is very important, Ray, you've got to read it. And I couldn't. So I got a month off, right? I had a winter holiday. I got time away from university, so I studied this work. I had to read up each of these bits and pieces. What I realised is that along with a student of mine, we'd proven this result 4 years ago. So I'd been staring at this proposition for about a year, 18 months. I'd already proven it, but I couldn't tell. It was the same thing. So it's actually quite a simple result, and we'll be using it later on. Anyway, so is this a problem with their work? No, it's not, because these guys are coming from a different space. They've got a whole other different range of theory and work that they're using, and they bring it all together. So they're working in a much more complex space of 5 or 6 different areas that they're putting together. And we're just focusing in on this one space. And in our one space, there's one way of writing something up. But they've got all of their other bits of theory that they're trying to tie together. So for the mathematicians, this is all good. They can have this. But we don't need this complexity. It's no good for us. It's what they use to arrive at their results. But, anyway, so that's the end of the rant. A lot of the material is inaccessible, and it's sort of unnecessarily so. I think a lot of the early work in the field was poorly presented. I don't think the hierarchical Dirichlet process people really understood what they were working with, and I see that from their empirical work. Their empirical work illustrates they're not really knowledgeable of the key results that they're dealing with. And there's also some equivalences between models that I'm not sure how well understood they are. So that's where we are. We're now ready to dive into some more meat of the theory, looking at these processes in a bit more. I've benefited, so Lancelot James has done, I think, all the key results here. So 20 years earlier it was Jim Pitman, and now it's Lancelot James doing a lot of these. I was very fortunate. He happened to examine Changyu Chen's PhD thesis, so we got communicating through there. So I was very fortunate to sort of benefit this stuff from him. So now we're going to jump into this theory. It's probably a good time to have a break. The first thing I'm going to do is give you a broad outline of what's to come. So firstly, we'll have a broad overview of things. Some of the theory we're going to skip. So it's in the slides, but I'm not going to give it to you. It's probably a little bit of extra unnecessary complexity. And then once that's done, we'll look at the major results. Now, some of these results I'm just citing. Well, in fact, quite a few of them I'm just citing the major results. And some of them, this is probably the most important thing for us to do here is, I'd call it Bayes' theorem for Poisson point processes. If Lancelot James were to catch me showing this to you, he'd probably strangle me because he's got his own version of this. But if I don't think, I still am struggling to understand his own version. All I know is it's correct and it does a lot more than what we do. But this is good enough. This is what I would call, this is good enough for our community. So, and it does all the work we need. So that's what we have.